Hello and welcome back to part two, dealing with origins of modern astronomy. In this segment, we're going to talk about some early Greek ideas and then move on to the Renaissance ideas. The Renaissance really took place from about the 14th century to the 17th century or so. And so Copernicus really kicks things off with coming up with an alternative model for the solar system, sort of transitioning us from Aristotle and the Ptolemaic models. And then we hit Galileo, Kepler, and Newton, which all contribute to our modern understanding of the solar system. So the basic idea with the golden age of astronomy was that, we started developing a model, right? Looking at the stars, trying to understand what motion in the stars meant, and looking at different parts of the night sky was able to tell us something about the Earth. Now, the idea that the Earth was round took a while to sort of catch on among many people, but it was not a new idea to the Greeks. So it's something that people had been speculating about and thinking about. So they were looking at, for instance, a ship moving over the horizon and disappearing as evidence for the Earth being round, relative position of stars on Earth changing, and then also shadows on the surface of the Earth. And in fact, the Greeks were able to calculate very accurately the shape of, the circumference of the Earth using different lengths of shadows. And I'm not going to spend too much time with that. But we had an idea, or at least the Greeks had an idea, that the Earth was round. But what we couldn't perceive at the time was the sort of the basic concepts of physics. Our understanding of like how fast we're moving, right? If I was at the equator today, I'm moving around the Earth's axis at about 1,000 miles an hour. I'm then moving around the sun at some velocity. I'm rotating within the galaxy, and the whole galaxy is expanding away from other galaxies at some velocity. So everything is sort of relative to your position, but the Greeks didn't really understand all of this, and so they felt that the Earth was probably still. And that was because sort of like if you got on a cart, right, and someone pulled you along, or on a horse, you'd feel your momentum would keep you from moving forward, and then you would eventually catch up to the horse. And the same thing happens in a car today. The Greeks didn't feel this lurching going on, so they felt like the Earth was still. And the other thing that they thought that they should see was a parallax, right? So this parallax is the idea, and I'll just flip over to this next slide really quickly and come back. I talked about this briefly before, is that if you look at a star out here, some distant star, from one position, it's going to appear to be in position 1 in the sky and correlate with position 1 for the Earth in its orbit around the sun. But if we are here in position 2 with Earth on the other side of its orbit, so halfway through its orbital period, the star looks like it has moved over to position 2. But nevertheless, relative to the whole system, it sits exactly in the same position that it's in. And so if you were to, fix your gaze on some particular, button or something on the wall, and you close one eye and you flip to the other eye, back to the first eye, back to the other eye, so looking at the same point with one eye open and one eye shut, you see it shift around. And that's because our eyes are separated by a couple centimeters on our face. And so if we want to see a parallax, then the Earth is separated by, what amounts to, it's just over 300 million kilometers from one side of its orbit to the next. And so presumably we'd be able to see a parallax. Well, it turns out that the stars, the closest stars, are not that close. And so that it's without a telescope or some other more accurate measurement, it's very difficult to perceive a parallax. So the Greeks then came up with a model by looking at the different planets, observing these objects in the sky, that put the Earth at the center. And we call this a geocentric model for the solar system, right? The Earth's at the center, and we'll look at an example of this on on the left-hand side here, the moon rotates around the Earth, orbits around the Earth, and then we step out and we get to Mercury, Venus, right? So Mercury to Venus, that's good. Now, the Earth used to be out here in the third planet from the sun, but now we're going to put it, switch it out for the sun. So now we put the sun where the Earth used to be, okay? And then we get to Mars and to Jupiter and to Saturn, and after that it gets pretty tough to see anything without a telescope. So this was the geocentric model for the solar system based on how we perceive things around us. But as we got a little bit better at making measurements and trying to predict the motions of the planets, we came up with what's called the heliocentric model. And that's shown here on the right. And this should be, it's not the heliocentric model, it's actually the geocentric model again. Sorry about that. So here's the sun. These are both the geocentric model. So this one is geocentric and this is geocentric. And I'll get to the heliocentric in a second. But if you want to swap out the sun and the Earth here, okay, that's really the big difference in between the heliocentric and the geocentric models. Okay, now the question you might ask yourself is like, all right, what drove some of the early models for the solar system, and what were some of the reasons why we had to go from geocentric to heliocentric? And one of those is the motion of Mars, or the movement of Mars in the night sky. You've heard probably of like fortune tellers and people who read palms talking about like Mars in retrograde, right? So really what they're talking about is the apparent motion of Mars in the night sky. And the apparent motion of Mars in the night sky is, in some cases, in reverse. So if Mars is outside of our orbit and we're moving past it, Mars should be going back like this, right? Always back like this. But there are periods in time when Mars actually looks like it's getting ahead of us, okay? And we call that zigzag. And so this is the path that Mars makes in the sky through the months, probably from May to August, right? Mars, Mars, Mars. We call that retrograde motion. And you can look at some YouTube videos on retrograde motion and I put some YouTube videos up here so you can go to those links if you're interested, but dedicated people take their telescope out during these months and take images of Mars and then make a collage to show you the motion of Mars. Well, to explain this, we had to come up with some kind of different model, and this is the Ptolemaic model that I'm going to get at. So here's that's where we're going. So here's what Mars looks like when we're looking at it, right? Out here in the solar system, that's what it looks like. Down here is the Earth, okay? And out here is the Martian orbit. Remember, it takes twice as long almost for Mars to get around 685 days or so for Mars to move around its orbit around the sun. So that's the Martian year, which is longer than ours. And so we're moving around faster in sort of the inner circle, the inner track. And we're also moving in a different direction here. So there are times, when Mars is still on this long straightaway, we're on the curve of our orbit, right? We're at the solstice, one of the solstices, either the December solstice or the winter solstice. Sorry, December or June solstice. And so we're actually moving perpendicular to Mars, right? We're not really moving parallel with or backwards with in either direction. And so it appears that Mars is actually in periods 1 or points 1, 2, and 3, right, is moving ahead of us. But then we come around the curve and we get to points 4 and 5. And because we're on the smaller path and we're moving more quickly than Mars, we zip ahead of Mars. And that's where Mars looks like it's moving backwards in the night sky right here. Okay, and then we get around the corner again over here, and so into August or so. and Mars appears to zip ahead again. And that's because relative to Mars, we're not really moving very fast, even though we're moving around our orbit. And so Mars zips ahead in the night sky right there. And so that retrograde needed some sort of explanation within the geocentric model. And so Ptolemy, who's sort of toward the end of the Greek, came up with a model that involved what are called epicycles. So here's the geocentric model: Earth in the middle. Sun is the third planet from the Earth, or third object from the Earth, I should say. And so to get the planets to move backward in the night sky, what he did is he gave them all epicycles where the planet revolves around some fixed point within its normal orbit, right? So the moon does the same thing, or sorry, the moon doesn't do the same thing. The Mercury does, Mercury, Venus, Mars, and Saturn all are circling around something, some point. Now, we know from physics that this doesn't make any sense, okay? Centrifugal force requires that there be another object in here, and there are no objects. But this made sense to them from their perspective of making these observations in the night sky, that different planets, different objects actually appeared to move backwards in the night sky or have retrograde motion. Okay. Now, the problem with the Ptolemaic model, so the geocentric model, there were two sort of issues. One is that trying to predict the positions of the planets with this model didn't work very well. You could kind of get it, but you were often off by a little bit, or sort of just getting worse at different periods of the year. Was actually really off, and then got a little better because the Earth is moving around its orbit as well. And the other problem is that you could explain retrograde motion in other ways. And so Copernicus is credited for putting the sun into the center of the solar system, and his model comes out later in his life, toward the end of his life, but he comes up with a model that explains retrograde motion by putting the Earth as the third position from the sun, Mars is the fourth, and the sun in the center. And this is called the heliocentric model. Now, we have to test this, of course, and so that's what different people were doing at this time during the Renaissance. So here's Copernicus's model, is about 1530. And we continue to test it through the 16th and 17th centuries. Kepler and Brahe, Tycho Brahe, was making very, very detailed measurements of the planets. He was collecting a lot of data, but he didn't really know what to do with it, or at least he hadn't done anything with it. And so at some point, Tycho Brahe ends up dying, and his student, Johannes Kepler, takes that data and actually, plots it up and makes some sense out of it. And we end up with some of Kepler's laws. So Kepler gave us the first law here, that each planet is moving around an ellipse. It's not a very eccentric ellipse, but it's moving around an ellipse. Okay. He gave us some geometrical relationships. We don't need to get into too much about the second law, that planets revolve around the sun such as that they pass over an area that is constant area but a different shape. And so basically this relates to the velocity of the planets, right? So the area in here where the planet moves a very short distance, but it moves it at and the area in here where the planet moves a much longer distance, so this is long and this is short. Okay, these areas are equal, and that has to do with how the velocity of the planet is going to change as it moves around its orbit. So, the short distance might move at a slower velocity, whereas at the longer distance you might move at a slightly larger velocity, but the areas through which they move are constant. Okay, and then the last one here, rule 3, which is that the cubed root of the square of the planet's period. Now let's remember what its period is, right? its orbital period, that's the time it takes for it to go one complete revolution around the sun, okay, is equal to the average distance from the sun. So if we take its period, the cube of its period, or sorry, the square of the planet's period, cube root of the square of the planet's period, sorry, okay, which is shown over here, so its period is proportional to essentially its semi-major axis, right? So the semi-major axis is the average distance we are from the sun, and so that makes sense. Then the farther you get from the sun, so Pluto and Neptune are much farther from the sun. Okay, so they have a longer period in years. Remember, everything is relative to Earth years. So whereas Earth, here's one Earth year, right? So Pluto has a period, that time it takes to get around the sun, that is close to, let's say, 850 Earth years, okay? And it has a semi-major axis that is, if we draw a line all the way over here, intersecting this, this is probably on a log scale, close to about, let's just say it's more than 10 astronomical units, right? How far is the Earth? Well, it's 1 astronomical unit, so we're more than an order of magnitude in distance from, say, Pluto is. So you're probably at about 3 AU here. Actually, Jupiter is at close to 5, so this should be probably should be closer to 50 AU. That makes more sense. Okay, 50 AU. So you're way out there in the solar system. Okay, and so those are Kepler's laws. And so he took Tycho Brahe's data and was able to kind of come up with an explanation for predicting where the planets are and understanding how they behave. We still needed to test and establish the model for the heliocentric solar system, and one of those big contributors was Galileo, and there are a number of major contributions he made. One of them is connected to sort of fighting off the church, right? The Catholic Church was very against this like non-Earth centered or non-geocentric model and didn't like the Copernican model. And so Galileo made a number of observations. One of them was that the moon had all of these interesting features on it, and he recognized the highlands, which are these white areas. Okay, but he also noticed what he thought were seas and all these areas here on the moon, which he called Maria. And he thought they were oceans. It turns out at some point they were oceans, but they were oceans of molten rock that are ages around 3.6 billion years. Okay, he was able to observe the largest 4 moons around Jupiter. Those were unpredicted. No one had seen those before. He was also one of the first people to use a telescope, although he did not invent the telescope. He built a number of them. He documented the phases of Venus, which I'll talk about in a minute, and he noted that the sun also had some unusual features on it. So these are sunspots in particular, these dark, cold spots on the sun that are rotating around and moving on its surface. All of those kind of went against church teachings at the time, although it's not a biblical kind of thing to look at the sunspots or talk about them. The church kind of made some statements about objects in space and celestial objects being smooth and uniform. And basically what Galileo was like, hey, none of these things are smooth and really uniform. Okay. On the right-hand side, you'll see one of his first telescopes, a very simple refracting telescope. The Hans Lippershey was the first to try to patent the telescope. So, first to construct a telescope is a murky area. First to try and patent one, which was happened in the 17th century, and quickly they evolved within 25, 30, 50 years to building pretty big powerful refracting telescopes. Until we get to the point when we start making reflecting telescopes. And that's Newton in 1665. He's working on some of the first reflecting telescopes, and I'll talk about those in a little bit. Galileo's early observations regarding the moon, shown here, these are watercolors of the moon's surface. And so he's basically looking through his telescope and drawing pictures, because today we're taking pictures, different kinds of pictures of the moon. Okay. He also recognized the phases of Venus and how those phases that we observe don't match up with what would be predicted for Venusian phases if you're looking at a geocentric model for the solar system, right? So at the top we see the Earth-centered model, or the geocentric model, and this is our epicycle, right? So Venus rotating around some fictitious point as it moves through its orbit around Earth. So this is the incorrect model, but what you would normally see then would be Venus in a new phase when it's totally dark, and then you would see Venus in various waxing and waning phases. So waxing phases, so you see this sort of partial illumination of Venus, but it never gets to be full, kind of like the full moon. So there's no full stage of Venus. If Venus is outside of the Earth, but between the Earth and the Sun, you're never going to see it fully illuminated, right? You're going to see it dark in its new position. You're going to see crescent positions, and that's it. But what Galileo said was, well, let me look at Venus, and he found that Venus does have a full position, right? It's full position just like the full moon. It has full illumination. It has a new position out here, and it has a whole series of different sizes of crescent positions or gibbous positions. So crescent is usually when you see this sliver shape like that, and gibbous is where you're getting more than 50% illumination out here. Okay, and our moon has the same thing. So here's your crescent shape, and there's your gibbous shape there. And so that was another sort of nail in the coffin for the geocentric model, and pushes us toward the heliocentric model. Okay, here are those four largest moons that Galileo observed around Jupiter: Io, Europa, Ganymede, and Callisto. And so these have to be some of the most interesting things out there in the solar system, I would say. Io is probably one of the most volcanically active objects in the solar system, more so than Earth, in fact. It doesn't erupt basalt. It has this sort of shiny yellow tint because it's erupting sulfide, so sort of low temperature sulfur-based minerals. And then Europa here is very tectonically active, so it's got lots of cracks and fissures, and that has to do with Jupiter's gravitational pull. It's distorting the moon's shape as the moon orbits the planet, and causing it to be, well, let's say, torqued around a little bit, right? And then finally, he looked up at the sun with his telescope. Not a real smart idea, but he found all of these dark spots. And these are cold spots that are created within the sun's electromagnetic, or sort of probably created by the sun's electromagnetic field. And they're spots that sort of orbit and circle the sun. And again, they were imperfections in what we see here as what we call the photosphere, right? That's the sun's surface. It's kind of a grainy, sort of dark and light, sort of patchy. In this area over here on the left-hand side, it's patchy, but it's sort of a dark and light, spotty surface of the sun, which would be, for something that's made of incandescent gas, it doesn't really have a surface, but it's what we would call the surface, the photosphere. Okay, and so these sunspots are cold spots within this photosphere, and so they're actually moving on the surface, and that would be another line of evidence against the kind of church teachings about celestial objects and how they behaved. Okay, Newton gave us a number of different laws, three main ones that come up in physics, right? The first, the velocity of an object is constant and in a straight path unless acted upon. Sometimes people refer to this as sort of an object at rest stays at rest. So if you were to throw in space, in a perfect vacuum, throw a baseball, it would go on forever and ever and ever. and it would go on in a straight line unless some other force acted upon it. Well, it turns out that if you're in our solar system, the sun, which is that most massive object, much more massive and larger than Jupiter, is going to have a force that it's going to act upon planets, and that planet is, or that force is the gravitational force, right? And so the gravitational force is equal to the mass of object 1, which could be the sun, times the mass of object 2 divided by the square of the distance between those two objects will give us the force, the attractive force between those two objects. And because there's a force acting here pulling the planet in towards the sun, it can never quite travel in that straight line that it wants to. So it ends up traveling in a lot of shifted little lines. So here the Earth moves off in that direction. Now it's moving off in that direction, and now it's moving off in that direction. And as it moves around its orbit, it's sort of the sum of two vectors, one force pulling in and one force driving it off out into space. The net motion then is the sum of those two vectors, which we end up getting this curved or elliptical pattern. Other laws that Newton came up with: force is equal to mass times acceleration. That one should be very familiar. And the third law, applied force produces equal opposite reaction. So basically, if you push on something, that something is pushing back. If you lean on your dinner table with your elbows, the dinner table is going to push back on your elbows, right? So equal and opposite reaction for every action that is taken. And so those are Newton's basic laws, but what he ended up being able to do is to sort of explain why the planets move in elliptical paths, right? This is important. Why do they have circular paths, and what holds them in their positions? So while Copernicus came up with a model that didn't require epicycles, right? Newton finally came up with a mechanism to explain why that model worked. Okay, and again, that acts as then a test to the whole hypothesis. All right, so we talked about some of the major features in the solar system in terms of sort of understanding the organization of the planets and the evolution. The golden age of astronomy is really that period in the Greeks, sort of 600 years before, and just maybe 100 years or 50 years or so after the death of Christ, where we see people coming up with models to explain the solar system, but not really coming up with the model that we have today. Those early models were based on trying to explain to some degree the retrograde motion of the planets and our perception of how the planets were moving, both our perception on Earth as well as our perception about what they were or where they were out in the solar system, and that gave us the geocentric model. And then it wasn't until we got into the Renaissance or the Enlightenment, potentially even, and started looking at alternative models for how the solar system worked, and came up with and tested to some degree the heliocentric model. So we'll move on to talk about motions of the moon, eclipses, lunar eclipses, and those sorts of things in the final